In the world of statistics, we often grapple with uncertainty. We seek to understand patterns and make predictions based on limited data. Bayesian estimation offers a powerful framework for navigating this uncertainty by explicitly acknowledging and incorporating our prior beliefs into the analysis. Traditional statistical methods, often called frequentist approaches, focus solely on the observed data. In contrast, Bayesian estimation allows us to combine our prior knowledge with new evidence to arrive at a more informed and nuanced understanding. This approach is particularly well suited for situations where we have some initial insights or assumptions about the phenomenon we're studying. This essay explores the fundamental concepts of Bayesian estimation, focusing on its application to the exponential distribution. We'll delve into the step-by-step process, compare it to traditional methods, and highlight its real-world applications. By the end, you'll have a firm grasp of how Bayesian estimation helps us make better decisions in the face of uncertainty. Before diving into the intricacies of Bayesian estimation, let's familiarize ourselves with the exponential distribution. This probability distribution is widely used to model the time between events that occur independently and at a constant rate. Imagine you're interested in understanding the lifespan of light bulbs. The exponential distribution provides a way to model the time until a light bulb burns out, assuming that the probability of burnout remains constant over time. Similarly, in a call center, the exponential distribution can be used to model the time between customer calls, assuming calls arrive randomly and independently. The key characteristic of the exponential distribution is its memoryless property. This means that the probability of an event occurring in the next moment is independent of how much time has already passed. Whether a light bulb has been burning for an hour or a day, the probability of it burning out in the next minute remains the same. This property makes the exponential distribution a suitable model for various real-world phenomena. At its core, Bayesian estimation revolves around updating our beliefs as we gather new information. It's a dynamic process of learning and refinement, where we start with an initial belief, observe data, and then adjust our belief based on the evidence. Imagine you're trying to estimate the average height of students in a school. You might have a prior belief that the average height is around 5 feet 4 inches. However, as you measure the heights of a sample of students, you gather new data. Bayesian estimation allows you to combine your prior belief with this new information to arrive at a more accurate estimate of the average height. This process of updating beliefs is formalized through Bayes' theorem, a mathematical formula that quantifies how our beliefs should change in light of new evidence. While the formula itself might seem intimidating, the underlying concept is intuitive. We adjust our confidence in a belief based on the strength of the evidence supporting or contradicting it. Section 4. Prior beliefs, where intuition meets data. One of the key distinctions of Bayesian estimation is the explicit incorporation of prior beliefs. These beliefs represent our existing knowledge or assumptions about the parameter we're trying to estimate. They can stem from previous studies, expert opinions, or simply our intuition about the phenomenon. For example, if we're estimating the average lifespan of a new type of light bulb, we might have a prior belief that it's similar to the lifespan of existing light bulbs. This belief could be based on the materials used, the manufacturing process, or other relevant factors. It's important to note that prior beliefs are not set in stone. They are simply our best guesses based on the information we have at hand. As we gather more data, our prior beliefs are updated and refined, leading to more accurate estimates. Section 5. The likelihood function, quantifying the evidence. The likelihood function plays a crucial role in Bayesian estimation by quantifying the evidence provided by the data. It tells us how likely it is to observe the data we have if a particular value of the parameter were true. For instance, if we're estimating the average time between customer calls, and we observe a short interval between two calls, the likelihood function would assign a higher probability to values of the parameter that correspond to frequent calls. Conversely, if we observe a long interval, the likelihood function would favor values associated with less frequent calls. The likelihood function acts as a bridge between the data and our beliefs about the parameter. It allows us to assess how well different values of the parameter explain the observed data.